Hey, this is Physics 2211, Lab number 2, Motion of a Falling Object by Karthik Chilkapati. So, our introduction, the purpose of this lab is that we are trying to compare the observational motion of a falling object. In my case, it's going to be a paper ball, to two computational graphs of the same motion, one with just gravity and one with gravity and drag. So to figure this out, we need some fundamental physics principles, and one of them that we have is the force of drag, which is negative bv squared times v hat. We need this to compute our drag force in our computational model, and then we have our position update and velocity update formulas to update our position as and velocity as our object falls down through in a vertical path. So the results of this experiment were that the observational data was more similar to the computational data with both gravity and drag rather than just with gravity. So our initial conditions for the experiment, I dropped the paper ball from a height of 1.42 meters and it started from rest of 0 meters per second. And our system is the paper ball and the surroundings are earth and we could also say gravity and air. Here's the code and where I inputted all the initial conditions. So first, our observational motion. Here's a video I recorded of me dropping the paper ball down to the floor from a height of 1.42 meters. I put it in the tracker and used the tracking feature to find the position of the ball throughout its path. And then over here, we created a position versus time graph and velocity versus time graphs in the y direction to see the motion of the ball. So our first computational model we're looking at is with gravity. Here's the code I created for this. Our time for the fall was 0.635 seconds, so that's why I put this here. And since we're just looking at gravity, my drag vector is going to equal 0 because we do not want to consider it in this part of the experiment. And gravity of the gravity force would just be the mass times gravity in the j direction. And it's negative because it's going down. So our F net is going to be our gravity force plus drag force. In this case, it would just be our gravity because the drag is 0. And then I use the position update and velocity update formula so it can update these two factors as the ball falls throughout its path. And then this is a graph that was generated from position versus time graph that was generated from this computation. The second computational graph was for gravity and drag combined. So everything is the same here except for that our drag force equation is going to be what we were given of negative b times the magnitude of the velocity of the ball squared times the the velocity hat of the ball. And then once you add gravity and drag force together, we get this new graph. As we can see that the end position is different for this one and it didn't go below 0. So comparing all of these things together, we can see that blue is going to be our observational data, red is going to be the one with just gravity, and yellow is one with gravity and drag. Here we can see that the yellow and blue lines are very similar, so this tells us that the observational data and our computational data with the gravity and drag force are more similar compared to just having gravity in our computational data. Sources of error for this would be that the paper ball may have not fallen in an exactly vertical path, but that's also why we set our axes back here in our observational to be a little bit tilted, but it isn't always perfect, so that can probably cause some sort of error. Moving on to the conclusions, which model predicts terminal velocity and what does terminal velocity mean for net force? We can tell that the model with both gravity and drag predicts terminal velocity because as in the velocity versus time graph, we will eventually see that there is sort of a asymptotal line that the graph curves to and it starts getting more flatter as time goes on. So this means that it's just reaching a constant velocity because our net force is going to equal 0. And when net force is 0, that means we reach terminal velocity. So this means that drag and gravity are both going to be equal at that point. Would the terminal velocity be the same if it had initial velocity? So the terminal velocity would not change in the end because we still have like the same amount of like gravity force acting on it. So it's just a matter of time of how quickly we get to that net force equaling 0. So terminal velocity will not change, but if we throw the ball with a downward velocity, initial velocity, then it would just shorten the amount of time that it would take us to reach that terminal velocity. And that is it. Thank you for your time.